Yes. Yeah. Yeah, that's a good idea. All right, let's talk about 1.1 then, very quickly. On the handout, I have pretty much the same steps. I think they're worded or numbered a little bit differently, but the same steps that I have on the 1.1 handout in Momentum, if you decide to print that. The steps for solving a linear equation are, this lists any restrictions on the variable. My handout doesn't have that, but I'm going to come back to that in a minute and tell you what that means. My handout starts with just, if necessary, clear the fractions and decimals. If you do have to clear fractions, then multiply both sides by the least common multiple of the denominators, or that would be easier just to say the least common denominator. After you've cleared out fractions and decimals, I don't usually clear out decimals because they're not hard to enter on the calculator. All right, I'll just work with decimals if I have them. Fractions are a little bit more cumbersome to type on the calculator. Plus, if you have an equation with a variable in the denominator, you can't enter that on the calculator anyway. So I do always clear fractions. Personally, I don't clear decimals. But after that, you distribute to remove the parentheses and combine like terms. Then you get all the terms with the variable on one side, all the terms without the variable on the other side, and then divide by the coefficient of the variable, and most importantly, check your solution. Anytime you can check your answer in math, do check your answer. Every time you factor, you should multiply it back together real quickly to make sure it gives you what you started with. Anytime you solve an equation, you can take what you think the correct answer is, substitute it back into the original equation, and make sure that it makes it true, because that's what it means to be a solution to the equation. Now, the examples that I want to show you in the book are from 82 to 87. Example 2 is a very good example. Actually, I think this is page 84 now. It's a very good example of solving a linear equation. You don't have time to write this down because I'm not gonna just read it to you, but you can see that the first thing you do is say that the common denominator of those two fractions is 6 and multiply both sides by 6. When you multiply both sides by 6, make sure you distribute the 6 completely. How many terms, this is a good question right here, how many terms are inside that bracket? That's the most common wrong answer. I paid you to say that, right? Just 2, because anything that's held together by multiplication is all part of the same term. Some folks want to multiply the 6 times the 1/2 and the 6 times the x plus 5, but that's all part of the same term. So just multiply the 6 times 1/2, and in the next step, you'll end up distributing the 3. Now do make sure you also multiply the 6 times the 4, because that's a different term. And here again, multiply the 6 times 1/3, but then just distribute 2. Don't multiply 6 times 2x minus 1. Clearing out the fractions is the hardest part of that process. After you clear out the fractions, you distribute, combine like terms, get all the terms with an x on one side, all the terms without an x on the other. If you end up with negative x, don't stop there. You're not through. You have to divide both sides by -1, and you get x equals -7. The book even shows you the check, and it is a little bit cumbersome to put -7 in the place of all the x's and work it out. But sure enough, the left-hand side comes up to be -5. The right-hand side equals -5. Since the left-hand side equals the right-hand side, -7 must be the right answer. I've had folks go all the way through that and then put down -5 as their answer. -5 is not your answer. -5 is what both sides equal if you put your answer into the equation, but your answer is the -7. That's an excellent example. Even typed out to the right-hand side in blue, it tells you step by step exactly what's what's done on each step. So look at that one. Example 3, I'm not going to, where is it? Original. I'm not going to clear out the fractions there. I just punched that on the calculator. Not really going to spend any more on that time on that one. Example 4. Ooh, I forgot to say something important. Very important. I think I typed it on the handout. Yep. How do you recognize a linear equation? What does it mean to be, for an equation to be linear? That's first degree. That means the highest power of your variable is 1. Now, later, actually, Wednesday, we're going to talk about quadratic equations, and then the highest power of your variable is 2. But you need to be able to distinguish, and you need to be able to think on the test, hey, this is a linear equation because it's first degree. This is a quadratic equation because it's second degree. You don't solve them the same way. Now, the thing that made me go back and say first degree is this example 4. I think this is on page 86 in the book. And remember, if you don't have a hard copy of the book, that's fine. In my math lab, you can go into the ebook and pull up the very same page. But the reason that this made me think first degree is the first thing you do is clear out the parentheses by multiplying. But when you multiply a binomial times a binomial, you get a second degree expression. Why is this a section on solving linear equations if it has squares in it? What do you think is going to happen, Ms. Klein? When you subtract 2y squared from both sides, right there, all of a sudden, you have a linear equation. Makes it a first term. What do you mean by that? You mean first degree? Yes, it makes it first degree after you subtract 2y squared from both sides, and then you can finish solving that one, and you can check it. So I wanted to mention that one because, yes, it has a y square. It's quadratic for a split second, and then it's linear again. The other big one that I wanted to mention, and you really need to look at these in the book. There's one just like it in the homework. If you have trouble, pull up the ebook and look at one just like it. This is an equation that you have to clear out fractions, but the fractions aren't just constant. It's not like you can just multiply both sides by 6. You have to multiply by the whole LCD, and based on your work in R.7, you should be good at finding the LCD. The LCD of all these fractions is just x minus 1 times x minus 2. So here's both sides multiplied by x minus 1 times x minus 2. We zoom out just a little bit. The left-hand side was just a single fraction. When you multiply it by x minus 2, the x minus 2's cancel and leave you 3 times x minus 1. They've gone ahead and distributed and called it 3x minus 3. On the right-hand side, how many terms are inside the brackets? 2. So you have to make sure you multiply that whole LCD times the first term and the whole LCD times the second term to cancel out those denominators. And from there on, it's easy. It's canceling out the fractions that's difficult. Difficult, more difficult than the other parts. I'm not going to say it should rack your brain terribly. Notice here we came up with x equals 4. And when you substitute 4 into the left-hand side of that equation, then, well, you get 3 halves. When you plug 4 into the right-hand side of the equation, you get 3 halves also. So this 4 does make the equation true. It is a solution. However, this number 1 I told you I would come back to, list any restrictions on the variable. That means when you solve an equation with fractions in it, you always have to check your answer. Not only is it just a good idea to check your answer anyway, but in particular, there's something you need to watch out for. What can you not allow to happen in a fraction? 0 where? in the denominator. You cannot have 0 in the denominator of a fraction, or else the whole expression is, what's that word? Undefined. All right. So on this number 5, example 5, what if we had worked and worked and worked and worked and we came up with x equals 1? I'd be so proud of you for doing all that work correctly. But if you circled x equals 1, it would be wrong. Why would it be wrong? It would blow up, actually, both of those fractions on the right-hand side. 1 would give you a 0 in the denominator, and you can't let x be anything that would give you 0 in the denominator. What else? Yeah, what else can you not let x be? 2. All right. So if we had come up with 1 or 2, we would have had to remember just to say, hey, can't use them. They blow up the denominator. Mark them out. If we had if there was nothing that would work, we'd just write no solution. Or the book uses the empty set symbol, which is 0 with a slash through it. That's a hard thing to remember, but if I brought my pocket watch, I would hypnotize you all so that whenever you cleared out fractions, you would always remember, bells and whistles go off, check to see if my solution makes the denominator 0. If it does, I can't use it. And that's probably example 6 on the next page, but I didn't bring it. I just wanted to talk a minute about clearing out fractions. All right, watch my video in Momentum if you need to. Follow the link to Khan Academy if you need to. But you're kind of remediating any weakness that you have on solving linear equations yourself so that we can go on to what you've probably had less experience with. On my handout, where did it go? First page. Oh, there it is. Nope. I had it just a minute ago. Ah, there it is. There were 2 things that I thought you may not have seen a lot of, and want a couple examples in class. Solving literal equations. Literal equations, another name for them is just formulas. We're solving formulas for a particular variable. If you deal with Excel as the spreadsheet software at all, if I want to find a formula for calculating the amount of money that I have in the bank when P dollars is invested at R% for T years, that's fine. That's how this formula is always given to me. I can just type into one column of Excel that this cell is going to equal P times 1 plus RT and type those numbers in and boom, it's good. However, if I need an equation to find the interest rate that I need in order to grow, let's say, $1,000 into $1,500 in 2 years, if I need to know that interest rate, then I need to know how to solve that equation for R. And that's all we're doing here. The steps are the same. If there are fractions, you clear them out. If there are parentheses, you clear them out. So the first thing I need to do there is distribute the P. P times 1 and P times RT. The next step on a linear equation with only one variable in it would be get all the terms with the variable on one side and all the terms without a variable on the other. Well, this doesn't have a term that's not a variable. That's all there is, variables. Still, there's only one that I'm trying to get by itself, and that's the R. So I want all the terms with an R on one side, all the terms without an R on the other. The only term with an R is already on the right-hand side, so why don't we get the others on the left-hand side? What do I need to move? This P right here, this term that doesn't have an R in it. How would I move it? There's no mathematical operation named move. I would do what? It's added to the PRT, so I'd have to subtract it. Subtract P from both sides. And that gives me the term with the variable by itself. But I don't yet have the R completely by itself. To have it completely by itself, I'd have to do what? Yeah, the P, the R, and the T are held together by multiplication, and to unmultiply, you have to divide. So just divide by the stuff you don't want with the R. You may not even write that step down. You may do that canceling in your head. But A minus P over PT is what you would type into Excel if you needed a formula for the rate. I can tell you the most common mistake here. Folks want to divide by the the PT to begin with. They want to divide too early. If I gave you, say, 2x plus 5 equals 9, you wouldn't start by trying to divide both sides by 2 first. You would know that you had to get that term with an x by itself before you could divide. The rules don't change. You've got to get the term with the R by itself before you divide. All right, one more. This example 2, I like to do it in class because it looks like a formula for finding an average in a class that has 3 tests and a final, and maybe the final counts twice. Test 1, test 2, test 3, count the final twice, add them all up and divide by 5, and that'll give you the average for this class. So what if I had already taken test 1, 2, and 3, and I wanted to calculate what I needed to make on the final in order to have whatever letter grade I wanted. If I wanted an A, I'd put a 90 in the place of A. If I wanted a B, I'd put an 80 in place of this A for average. So what if I wanted on an Excel spreadsheet a formula that would calculate for F, the grade on the final, for any letter grade that you wanted? You'd have to be able to solve that equation for F. What's the first thing you would do? That's the first thing in the blue box at the top. Clear out the fractions. Multiply both sides by 5. When you multiply the right-hand side by 5, the 5s are going to cancel. That's what you wanted to happen. So you have 5a equals little a, b, plus c, plus 2f. Notice in formulas, capital letters and little letters aren't the same thing. So you have to be careful when you're dealing with formulas. This capital A and little a are 2 different things. Then what? Well, which variable am I solving for? F, so I need to get all the terms with an F on one side. I only have one term with an F, and it's on the right-hand side. So I want all the terms without an F on the left-hand side. How do I get them there? It has a lot to do with something. Let me tell you what this would be like, Wilson. If I wanted a 90 in a class that, or a 90 average in a class that had 5 tests, when I multiplied both sides by 5, this would be 450. 450 is the total number of points that I'd need in order to get an A. All right? Yeah. Yeah. To solve that for F, first I would need to subtract my first 3 test grades from that. Like I said, if you wanted an A, that would be 450. You would be subtracting off the points that you already have from the points you need to get an A. That would give you the remaining points that you had to earn. But if your final is going to count twice, you would take that remaining number of points and just divide it by 2. Absolutely. And that's a big thing that got me through a lot of math. If I'm not sure what to do with variables, I make up a problem like it with just numbers in it and say, what would I do if these were just numbers? And then whatever I would do with just numbers, I do the very same thing with the variables. But, you know, if you saw this formula in Excel, you might not realize what it was about or how someone came up with it. But it makes sense if you start thinking about, well, to get a B, I'd have to have an 80 average, multiply both sides by 5, so I'd have to have 400 points. Let's subtract off the points that I already have, and then divide by 2 since the final counts twice. Makes sense where that formula comes from now. All right. I said there were 2 things that I wanted to mention other than just solving the linear equations, and you'll have to look at those examples in the book if you need them. Solving literal equations, and then one-word problem, because you have one very similar to this in the homework. It's also an average problem because, let me just tell you this, if you're coming into the final exam in college algebra and you have and you come up to me and say, what do I have to make on the final to pass the class? I'm going to say, you can't pass the class unless you can figure that out. At the end of college algebra, you should be able to figure out what you need on the final to pass the class or to make an A, B, or C. So let's practice one more. Going into the final, which will count as 2/3 of the final grade. This one's a little bit harder because it has a fractions in it. Man, that would be rough. Final exam counting you get 2/3 of your grade in one day. The whole other 15 weeks of the semester just count 1/3 of your grade. That'd be terrible if you were kind of feeling bad that day. But I digress. Mike has test scores of 86, 80, 84, and 90. What does he need on the final in order to earn a B, which requires an average score of 80? Well, it's going to be very similar to this. If the final's 2/3 and these other 4 tests, what part of the grade do they count? Just 1/3. All right, so how would I find his average? Let's say he's already taken the final and he made a 90 on it. How would I find his average? Well, I've changed the problem for just a minute, though. Instead of him trying to figure out what he needs to get a B, I'm just trying to figure out how I would find his average if he had made a 90 on the final. Would I add the 90 in with the 4 tests the previous 4 tests that he's taken? That would get the average of his. But what are you doing with the 2/3 and the 1/3? Say he made a 90 on the final. Well, the final counts 2/3, though. You're closest of anybody who's spoken yet, but you just got your numbers in the wrong place. The final counts 2/3. All those other tests count 1/3.
So you'll add all those together and say plus 2/3.
Yes, you multiply the 2/3 times his final exam grade. You definitely do that. Now, Wilson, you were right in that I need the average of those 4 tests, so I should add up those 4 tests and divide by 4. But those only count what part of his grade? So I'd have to multiply that times 1/3. And then multiply his final times 2/3, and that would give me his average. All right. I need to do the same thing, but I don't know the final. I just know he wants to end up with an 80. So help me come up with the formula here. First thing I need to do is what? Add those 4. 86 plus 80 plus 84 plus 90. And then what? Divide by 4 because I want the average of those. And then what? That counts as 1/3 of his grade, so I'm going to multiply that times 1/3, and then what? Two-thirds of the thing that I'm looking for? Two-thirds, well, I just said a minute ago, let's play like he made a 90. We're through playing like that now. We're trying to find. Yeah, X or F for final, whatever variable you want to use. That's what has to equal 80 in order for him to get the B in the class. 1/3 of his current average plus 2/3 of his final has to come up to 80 points in order for him to get the B in the class. Now, we can simplify this a whole lot. We don't have to clear out fractions right this minute. We can go ahead and find out what this average of the first 4 tests is. Has someone punched 86 plus 80 plus 84 plus 90 divided by 4? 85? Is that, Kevin, did you get something different? I think it is 85. Just punch it one more time. So this is 1/3 times his current average, which is 85, plus 2/3 of his final has to equal that 80. Okay. Did you hit the well, no, you would have gotten a crazier answer than 83 if you hadn't hit the equals after you added. Wake up. Um, 86, 80. No, it doesn't, Kevin, because you're adding an 86 and an 84. It's the bifocals. We're not getting old. We're just getting smarter. That's true. I feel much wiser than I did 20 years ago. All right. Listen. All right. We have 2 choices at this point. I could multiply 85 times 1/3, but I know 3 won't go into 85 evenly, and it would give me a decimal going on forever. I could do that because I have a calculator, and it can keep up with the decimals for me. What I don't want to do is round. If I round, then I may come up with not the exact answer that I need for the final. So instead of punching that and getting a repeating decimal, I could clear out the fractions now. I could multiply both sides by what to clear out the fractions? By 1/3. It's always good to have 2 colors of pencils in here. And let's multiply both sides by 3 to clear out the fractions. Now on the left-hand side, how many terms are there in that parentheses? Nope, just 2, because terms are separated by addition and subtraction. And this is the only addition and subtraction, so these are the 2 terms. I need to multiply the 3 times this term and the 3 times that term. When I multiply 3 times 1/3, what does that give me? Just 1, and then the 1 times 85 is just 85. You would have gotten back the same 85. Yeah. And what about 3 times 2/3 f? What would that leave me? 2f, because the 3's would cancel. 85 plus twice the final has to add up to 240 points. Yeah, so how many points does he have to earn on the final? How many total points? 85 minus, or 240 minus 85. And since the final counts twice, and he has to earn 155 points, he only needs to score a 77.5 on the final in order to have a B. Yeah, it'd be great. I believe in working hard in the beginning so that you can slack off at the end, if possible. Slacking off at the beginning and trying to catch up at the end. Everybody who over 25 say that doesn't work. That does not work. You cannot fail the first test, which is supposed to be the easiest test, and go, I'll do the practice test next time. That's one of the most irritating sentences in my existence. When somebody makes a 30 on the first test, and on the way out the door, I hear them laughing and saying, I'll do the practice test next time. Should have done it this time. All right, in the homework, 1.1, most of your problems are just solving equations. You have 1 or 2 formulas to solve for a certain variable, and you have 1 or 2 word problems. Let's go on to 8.1, which is not just solving linear equations, but solving systems of linear equations. Still, the highest power of the variables in all of our equations is 1, but sometimes in real life, you're working under more than one constraint. You're trying to satisfy 2 bosses, or you're trying to accomplish 2 things. For example, maybe you're in manufacturing and you want to calculate the size of a box that would hold the most stuff, but use the least cardboard. That's a whole industry, folks figuring out what size box holds the most stuff, but minimizes the amount of cardboard you need because that cuts cost. So what if you're solving 2 equations? You can solve 2 equations in 2 variables. That's called a system of equations. Actually, there are 3 methods for solving it. Look at this picture at the top of the next page, and then we'll come back to this big paragraph. Where's that picture? Right here, straight out of the book, figure 1. There are 3 things that can happen when you solve 2 equations. Now, these are linear equations, so when you graph them, you get a straight line. And if you graph 2 straight lines on the same graph, there are 3 possible things. Did you see that, Courtney? I just spit everywhere. Yeah. What if I spit and it shocks me? There are 3 possible things that can happen when you graph 2 lines on the same graph. Number 1, and most often, the 2 lines will cross in 1 point. That 1 point is your solution. You're looking for the point, the ordered pair that satisfies both equations. That's the point that's on both lines. So if the line crosses in 1 point, that is the point that's on both lines. It's the solution. And that's what happens most of the time. But every once in a while, You can graph two lines and find out they don't cross anywhere. What does that tell you about number of solutions to that system? If they don't cross, there is no solution. And that's basically all you can say. There's no solution. The other thing that can happen is, what if you had two equations that gave you the same line? What does that tell you about the number of solutions to that system? There are infinitely many solutions. Now, I'm not saying all real numbers. I'm not saying anything you want to plug in makes these equations true. I'm just saying anything that makes one of them true makes the other one true, because if you graph them, they're the same line. All right, going back to that other paragraph at the bottom of the first page. A system of equations consists of two or more equations and two variables. We will only look at linear equations in two variables. The solution of the system is the ordered pair x, y, which satisfies both equations. It has to make them both true. If a system has a solution, it's called consistent. And if it has no solutions, it is called inconsistent. I used to not mention those words in class, but they ask in my math lab, so I had to go ahead and tell you what consistent and inconsistent are. Inconsistent just means no solution. Consistent means at least one solution. The three things that can happen if you graph two lines are that the two lines can intersect in one point. That one point is the solution. The system does have a solution, therefore it's inconsistent. There's one other word you need to know in number one and in number two. Correct. Do I have it labeled wrong?
No.
Oh, okay. Oh, I said it wrong. I wrote the right thing, said the wrong thing. Oh. If there is any solution, one or infinitely many, then the system is consistent. If there is no solution, if the lines are parallel, the system is inconsistent. If the system is consistent and the lines only cross in one point, then the system is said to be independent. If you get the same line, that's number 3, the system is consistent, and also the equations are independent. Anything that makes one of them true makes the other true because ultimately they're the same line. And I said the wrong thing again, didn't I? With my finger on the word dependent, I said independent. Huh? And then I said what I said wrong. That's because you and I are about the same age. Okay, what is typed is correct. Back to the picture one more time. If there's one solution, maybe I'll write it right here. If there's one solution, the system is consistent and independent. They're not the same line, so it's independent. If two equations do give you the same line, there are solutions, so the system is consistent, but really they're the same line. What makes one true depends on what makes the other one true because it's the same thing. That's consistent and dependent. Is there any solution? No. If they don't cross at all, there's no solution, and that's inconsistent. It's the only case that a system is inconsistent. No, that's not what consistent and inconsistent means. Consistent means has at least one solution. Inconsistent means doesn't have at least one solution. You're thinking consistent as meaning does the same thing forever. Yeah.
Not the math class.
No, this has a special meaning in math class. All right, so there are three methods that can be used to solve a system. One is by graphing and looking at the graph. The hard thing about that method, though, is identifying if there's one solution, identifying exactly what that point is. What if that point had fractional coordinates? What if that was the point 1/3, 1/2? That would be pretty darn difficult to identify on a graph. If you were using graph paper and it crossed at exactly 4, 5, you might be able to figure that out. But if it crosses at a point with fractional coordinates, you might not ever figure out exactly what makes it true. So this graphing method gives us a good mental image of what the system looks like, but it's not the most efficient method for solving the system. There are two other methods that are more efficient for solving equations, and one is substitution, the other is elimination. Let's talk about substitution first. In that example, I have 3h equals 24 and 2w plus 5h is 80. That's my two equations. I have two variables, w and h, but the first equation only has an h in it. If you tell me 3h is 24, then immediately I know something. What is it? H is 8. This equation is very easy to solve by substitution because you can immediately get the value of one of the variables. Now I'm solving the first equation for h. I had 3h is 24, divide both sides by 3, and I get h equals 8. Then substitute that in the place of h in the other equation. Just put it right there. 2w plus 5 times 8 equals 80. 5 times 8 is 40. If I subtract 40 from both sides, I just have 2w equals 40. And then divide both sides by 2, and I have w equals 20. So that system was pretty easy to solve because this first equation only had one variable in it. Ooh, if this was a multiple choice test, would you say it has one solution, two solutions, no solutions, or infinitely many solutions? That's what I'd put for A, B, C, and D. It only has one solution. I was afraid someone might say two solutions, 8 and 20, but 8 and 20 aren't separate solutions. They're the two parts of the one solution. This system only has one solution, which is 8, 20, and unless otherwise specified, ordered pairs are in alphabetical order. If I don't tell you for some reason the W comes before the H, then you should assume the H comes before the W, and it does matter. The other thing you're going to have to say in my math lab is this system consistent or inconsistent? If it has even one solution or infinitely many solutions, it's consistent. If there's only one solution, then you're saying These two equations are different. There's one point where they intersect, but they're not the same equation. What makes one true does not make the other true, so is it dependent or independent? Independent. You graph those two lines independently of each other. There just happens to be one point where they cross, but this system is definitely independent.
So when you plug in that 8, that's your first number.
Yes. The first number in your ordered pair is your H, and the 20 is your W. So if you wanted to check this in the first equation, you don't have a W in it. Just put 8 in place of H and see if it makes the equation true. 3 times 8 is 24, so it definitely makes the first one true. See if it makes the second one true. Put 20 in place of W and 8 in place of H, and you would have 40 plus 40 equals 80, and that's also true. Did that answer your question, Ms. Courtney? Okay. So good choice for substitution. I said see also page 44, page 544, example 4. Let me see if I brought that one with me. Example 4. No, I don't have it with me. But I can make up something really quickly just like it, because there is one other thing I want to show you. You have it? Go ahead.
2x plus 5 make 4x plus 5.
See if I wrote down what you said. Okay.
Just leave that for one up.
Yeah. All right. This is a tiny bit more difficult than the first example because both equations have two variables in them. I can't just look at one of the equations and go, well, obviously x is blah, 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 or y is blah, blah, blah. Can't do that. However, it is easy to get one of the variables in one of the equations completely by itself. In which equation would it be easiest to get one of the variables by itself? The first or the second? The first one. And which variable would be easiest to get by itself? That y. Even though I can't tell you the numeric value of y, I can tell you what y equals just by subtracting 2x from both sides. Y has to equal 5 minus 2x. Now, in this first example, I found the numeric value of h, and I put that number in the place of h. Well, in this one, I don't know the numeric value of y, but that's okay. I can still substitute this whole expression in place of y in the other equation, and I'll have an equation that only has one variable in it. That's the goal, because I can solve an equation that has one variable in it. So take that whole 5 minus 2x, put it in place of y in the other equation. Negative 4x plus 6 times, I'm going to need parentheses here, 5 minus 2x equals 12. And then I just have one single linear equation with one single variable in it. It's like 1.1. I don't know. You got ahead of me. Let me catch up. I got 9/8.
Oh, yeah, there. That's 16.
That's when I subtracted 30 from both sides. 12 minus 30 is -18. Mr. Casey, you were frowning at that. Do you need to ask me something? Got it? Okay. That would be very difficult to identify by graphing. If I was trying to solve this by graphing, I probably never would get that x is exactly 9/8 or 1 1/8. So I would have had to have used a different method. I still only have half of my answer here. I have the x coordinate. I don't have the y. The easiest place to get the y is in the equation where you already have the y by itself. So I'm going to put that 9/8 in place of x and have y equals 5 minus 2 times 9/8, or 5 minus 9/4, or 5 minus 2 1/4 is 2 3/4, which is 11/4. If you don't do fractions in your head, what have I said? Get a calculator with a fraction button on it. Don't miss these problems because you haven't yet learned to add and subtract fractions. At this point in your life, just get a fraction button. Just a reminder from the syllabus, you cannot use cell phones on the test, so make sure that's not where your fraction button is. You can pick up a calculator with a fraction button for $12. You cannot use your cell phone on the test. All right. This again is an example of a system that has how many solutions? One solution, and it is the ordered pair 9/8, 11/4. And I'm not going to write it down again, but that system is consistent and independent. Consistent because it has at least one solution. Independent because the two lines aren't the same. Now that looks like a pretty good method. If we have one method that works, why would we want another method? Well, you could do all the problems on the test by substitution, but I think you would find that on certain problems, a different method is the easiest. You practice until you figure out which method is easiest to use on this problem. The reason substitution was so easy to use on this first example was one of the equations only had one variable in it. The reason it was pretty easy to use in the second system is it was easy to get that y by itself. But what if we had 2x plus 3y equals 5? If we solve for y, all of a sudden we would have fractions to substitute into the other equation. I'm not fraction phobic. I could do it, but it's not the easiest way. Let's talk about an easier way when you have fractions. Or when it's not as easy to get one of the variables by itself.
Let's say, like, when I first broke that one down,
Mm-hmm. Uh-huh.
So what I do, I thought I could get x.
How?
I multiply.
That's method 2. That's what we're doing next. That's the elimination method. So you recall that from a previous life. Yeah, and it's great. Number 24, I probably would not want to do this one by substitution because no matter which variable I tried to get by itself, I'd have to divide by its coefficients and I would have lots of fractions to plug into the other equation. I could do it, but I'm just trying to not have to. So Wilson's idea was either we could multiply by something that would cause the x's to cancel, or we could multiply by something that would cause the y's to cancel, or we could clear out fractions. We have lots of options here. We could clear out fractions first. But something kind of cool happens on this problem. If I was going to try to cancel my y's, I would have to say 4 and 5 both go into 20, so I'd have to make one of these become a positive 20 and one of these become a negative 20 in some legal manner, not just erase and put a 20 there. To do that, I'd have to multiply the top equation by 5 and the bottom equation by 4. Whatever I do to the left-hand side, do the same thing to the right-hand side. However, I may notice I'd get smaller numbers if I cancel the x's instead. 2 and 3 will both go into 6. So if I could make one of these be a positive 6x and one be a negative 6x, my x's would cancel. You can do either thing. I always go with the one that would result in the smallest numbers possible. So what could I do to both sides of the first equation in order to make its coefficient 6x? Sure, multiply by 3. That just so happens to do something nice on the right-hand side as well, because 2/3 times 3 will give me a whole number. So that first equation is now what? Yep. 2. Yes, 2. You see why? Okay. Yes, that's right. 6x plus 12y equals 2. Now, in order for the x's to cancel, the coefficient of x in the next equation has to be negative 6. So what would I have to multiply both sides by? Negative 2. And then what has my second equation become? Equals? Right. I caused what I wanted to happen to happen. I had to figure out what I wanted to happen and then the legal way to make it happen. Oh, that's a good lesson in life. Figure out what you want to happen and then the legal way to make it happen. I might need that on a sign. My x's do cancel like I hoped they would. When I add those two equations together, I get 22y equals 22. Therefore, y must equal 1. Don't forget that that's only half your answer. That's the y value in your answer. But then you have to go back and get your x value. You can use either original equation. It doesn't matter. When you check your answer, it does matter that you check your answer in both equations. But when you're just trying to find the other half, it doesn't matter which equation you use. I'm going to use the one that's closest right there, and the one that doesn't have a fraction in it. Put 1 in place of that y, and I have 3x minus 5 times 1 equals negative 10. I hate that I wrote on my original problem. That would get my knuckles wrapped at a nunnery. But I already have. Add 5 to both sides and divide by 3. So this system has one solution, and it's the ordered pair negative 5/3, 1. They actually what? You know what? The better you get at math, the more decent all of it becomes. Calculus is decent now. It was horrible. It was the stupidest thing ever when I was an undergraduate, but then all this. No, actually, when I taught one semester of high school and a kid had a loaded 45 in my room one day, all of a sudden calculus seemed like something I needed a master's in so that I could leave the high school. All right. We've had 3 examples now. 3, I didn't find out until the next morning faculty meeting. Principal stands up and goes, "Oh, by the way, Gary did have a loaded 45 in class yesterday." We've done 2 examples where we got 1 solution. What does that mean? It was consistent or inconsistent? Consistent, and all 3 of them, the lines were different lines, so the system was also independent. We need to see what would happen that would cause us to see that a system was either dependent or inconsistent. That's what's going to happen on the next 2 examples, and we need to do them super fast. Number 26 could be easily done by substitution. That first equation, I could either get the x by itself or the y by itself with no big deal. And so if you do it that way, it's fine. Or what could you multiply the first equation by that would cause something to cancel when you added it to the second equation? By 3. All right, that's pretty easy to figure out. Multiply both sides by 3. And my first equation now has become what? 15. 3x minus 3y equals 15. The second equation doesn't have to be multiplied by anything. The coefficient of x was already negative 3. But something strange happens here. When you add those 2 equations, what is the resulting equation? That's not an equation. What? 0 equals 17. The resulting equation is 0 equals 17. On what planet is that true? Maybe dwarf planet Pluto, but not Earth. What do you think that means these 2 lines would look like if I graphed them? They're parallel, which means what about number of solutions? No solution, which means what about consistent, inconsistent? Inconsistent, and if it's inconsistent, it's neither independent or dependent. It's just inconsistent. So no solution because the lines are parallel. But the button you click in my math lab is the inconsistent button. All right, number 30. What could I multiply the first equation by that would cause the x's to cancel? Nope. Negative 3. So that my first equation becomes what? Negative 9x plus 3y equals negative 21. And I don't need to multiply the second equation by anything because the x's are already going to cancel. But what's my resulting equation? Everything cancels is not an equation. 0 equals 0. On what planet is that true? Every planet. 0 equals 0 no matter where you are. What does that mean about number of solutions? Infinitely many solutions. No, but let me come back to that in just a minute. Infinitely many solutions. Anything that makes one of them true makes the other one true because if you graph them, what? They're on the same line. And in terms of consistent and inconsistent, that would mean inconsistent means no solution. Consistent and dependent because they're the same line. What makes one of them true depends on what makes the other one true. But in my math lab, there's going to be one other box, and I'm going to show you what to put in that box. I can't remember exactly how it's laid out. I think the directions are solve the system. If it is consistent and has one solution, type the ordered pair. If it is inconsistent, there's just a button beside the word inconsistent that you click. But if it is consistent and dependent, there's going to be this box. This is called set notation, and all of it's typed for you except for what goes in the box. Here's the way you read set notation. This is the set of all ordered pairs X, Y. That vertical line means such that Y equals blah, blah, blah. That means I want you to get one of these equations in slope-intercept form, Y equals blah, blah, blah. And that is the solution, or that contains the solutions to both equations, because they're the same thing. If you solve for Y in both of them, you'd get the same answer. But just to get what I need to put in that box, take one of the equations and solve it for Y. You would subtract 3x from both sides and then divide by -1. I'm going to turn it around to 3x minus 7. I don't know that my math lab would count it wrong if you put -7 plus 3x. It's the same thing. But I'm pretty sure that it'll tell you the answer is 3x minus 7. And that's what goes in the box. All that big fancy set notation is saying is any ordered pair that satisfies this equation satisfies both of those equations because they're all the same thing. No, that's not the solution. If you write the ordered pair 0, 0, would it check 3 times 0 minus 0 equals 7? No, 0, 0 is not the ordered pair. Don't type that for the answer. It's just the resulting equation which tells you what the answer is. Infinitely many solutions or consistent and dependent, but then you have to solve for one of the variables and put it in that box. Now, I'm not sure about this, so I'm telling you to watch out. I think that in this set notation, they'll always have Y equals, so you solve for Y and type in the expression for Y. But pay attention, if they ever had X equals, you'd need to solve your equation for X. All right, we have 5 minutes to do a word problem. Thank goodness I've already drawn the box for you. We are only going to talk about, well, maybe only talk about one kind of word problem. Maybe we can just set them both up and leave them for you to solve. But the two kinds of equations or word problems in this section are mixture problems and investment problems. Really, they're all mixture. Either you're mixing peanuts and cashews or you're mixing 401ks and IRAs. You're still mixing two things. So these charts are your best friend. Now, if you can do this problem and get it right the first time without making a chart, more power to you. I'm not going to come around and make sure you have a chart on your paper. But for those folks who have always struggled with word problems, these help you organize your information. In the left-hand column, put the things that you're mixing. Store sells cashews for $5 a pound and peanuts for $1.50 a pound. The manager decides to mix 30 pounds of peanuts with some cashews and sell the mixture for $3 a pound. Sounds like he has some cashews he needs to get rid of. So he's going to mix it with some cheap peanuts and sell it less expensively. So the things that I'm mixing are the cashews and the peanuts. Now, you need to know the words that go across the top of here. Each of these columns represents something that it's important for you to know about the cashews and the peanuts and the mixture. What's important for you to know? What's relevant in this problem? How many pounds there are. All right. So I'm going to label this first column number of pounds. What else is important about these nuts? Price per pound. And let's just say you were buying 3 pounds of something that cost $4 a pound. What do you pay? $12. You multiply price per pound times number of pounds, and that gives you the total price or total cost. That's the hardest part of this problem, just figuring out what to put on your table. The cashews sell for $5 a pound, so put it in that box, price per pound of the cashews. The peanuts sell for $1.50 per pound, so put it in that box. The mixture is going to sell for $3 a pound, so put it in that box. What's the 30? Is it? That's pounds of peanuts. That's not pounds in the mixture. That's not pounds of cashews. Read the problem carefully. It says 30 pounds of peanuts. The question is, how many pounds of cashews should I use? So it makes sense to let that be X. The thing that I'm looking for be X or C. So I know the total cost of the peanuts. If there are 30 pounds at $1.50 each, that's going to be $45. Just multiply straight across. What's going to be the total cost of the cashews? 5 times however many pounds I use, 5 times X. But in order to have the total cost of the mixture, I have to know how many pounds are in the mixture. Well, if I have X of these and 30 of those, how many do I have in all? X plus 30. And now I know the total cost of the mixture is 3 times X plus 30. If you use the chart, the equation is always staring at you right there in the last column. The cost of the cashews plus the cost of the peanuts equals the cost of the mixture we need 22.5 pounds of cashews.